So this is our second lecture in vapor power cycles. The last lecture was really a review of the Carnot vapor power cycle, which you were, a review from Thermo 1, as well as a review of the ideal Rankine cycle. That should have been covered, was covered in Thermo 1 as well. The idea is that you have four components, just go ahead and do them from memory. You can call it a boiler or a steam generator. You have a turbine, you have a condenser, and you have a pump, all right? And then out of the boiler, typically state one, and then out of the steam turbine, the steam is at state 2, out of the condenser, steam is at state 3, and out of the pump, steam is at state 4, or the working fluid, if you want to just call it that, is at state 4. Now, the ideal Rankine cycle is that this is now saturated liquid. How about the Carnot? What state was saturated liquid? Not state 3. What state was saturated liquid in the Carnot? 4, yeah. And we had a very unhappy pump for the Carnot cycle. So we have now a happy pump. Pumps like liquids. Okay, so it's fed saturated liquid. All right, we bring in all our heat into the working fluid. And for the Carnot, the working for all of QH comes in, or QB, comes in at a temperature TH. All right. Likewise, in the condenser, I'm going to show it this way. I'm going to QC, it's coming out. I know sometimes I have a negative sign on it. You just have to watch your signs. But it's rejected, and that's all rejected at the fluid at TL. Right? All right. Okay. I don't know how far we went in solving a problem with the ideal Rankine cycle. So we want to go ahead and say, here is a Rankine cycle problem. So we have steam or water is our working fluid. It's an ideal. What does that word ideal on the Rankine cycle mean? The turbine and the pump are reversible. There are no irreversibilities in the turbine or pump. Saturated vapor enters the turbine at 8 megapascal. So if I just go back to that schematic, this is saturated vapor. And the pressure, P1 is equal to P4, is the 8 megapascal. Last time I emphasized, hey, how many bar is 8 megapascal? 80, you're right. Now get good at that conversion and avoid it. Only a few had that conversion error on an exam, but it'll just knock points off. All right, or 8,000 kilopascal. So 80 bar. Okay. Let's continue to read the problem. Then saturated liquid enters the pump. That's the standard assumption. It's a happy pump. It's a Rankine vapor power cycle at a pressure of 20 kilopascal. So we go back here. The pressure of the condenser is the pressure at state 2, the pressure at state 3. That's all 20 kilopascal. Just like I could put pressure boiler is equal to pressure 1, equal to the pressure at 4, equal to 8 megapascal. All right. Let's look at our problem again. Determine the work developed by the turbine and the pump. Well, lowercase WT, because look at the units, kilojoules per kilogram. And that's, we anticipate, will be a positive answer. And then WP for the pump, and yes, I'm going to anticipate a negative in the sense that the pump is not a work producing, it's work consuming in kilojoules per kilogram. Part B, what is that heat transfer to the working fluid in the boiler? Q sub B. That, and we anticipate, is positive into the working fluid. And then what about the heat transfer in the condenser? Q sub C, and again, I anticipate a negative answer for that. I want it heat transfer into the device, but it's really out of the device, and so it's going to be a negative answer. Then the thermal efficiency, cycle thermal efficiency, how do we calculate that? Well, we get W net, that's what we wanted to achieve, net power out of the cycle, and we divide it by what did you have to purchase? You had to purchase the heat in the boiler, by burning a precious fuel. You had to burn that fuel, so the heat come out of the fuel. This W net is equal to W of the turbine plus the W of the pump, but because it's negative, it's actually going to reduce it's a negative quantity. Maybe this is, I don't know, 500 kilojoules per kilogram, and this is 5 kilojoules per kilogram, indicating that it's 495 kilojoules per kilogram positive out of the cycle. All right. A lot of times you'll have a sign error, and it'll be traced back to something like you added. That's wrong, okay? You add something that's a negative quantity or subtract a positive quantity. Okay. Then we do the backwork ratio as the other metric of interest. It's like, what came out of the turbine? Some precious work. I'd like as much of that to get to the electric generator, but a fraction of it has to go back into the cycle to run the pump, and so that's how much has to go back to run the pump. We put a minus sign on that to get rid of the minus sign in front of the minus. So anyway, it's positive over positive. If you just run with these numbers that I just put, that's 500, and then you had the 5 go back, right? Okay, so what percent is this? Here's a clicker question. Is this 10%, 1%, 0.1%? Answer A, B, or C. For these numbers, what is the backwork ratio? Not quite 100%. All right, so there you go. So when you solve these problems, break them down into steps. You want to have a schematic. We covered that. You want to have a property diagram to help you. A TS is the preferred property diagram. Get a table of properties. In the table of properties, everything really boils down to the H's, but a lot of times you have to use the S's to get the H's and the quality to get the H's. So, and then get a table of the transfers, the Q's and the H's, the energy transfers for each of those components. Tabulate, bookkeep, make sure that you're organized so you can check your work. Check that Q net is equal to W net. True? If it's not, look for an error. I do it all the time. It's like, okay, I need to double check my work. If I don't have Q net equal to W net, I have an error. And then calculate these metrics of interest. This would be, I know I put it into an Excel sheet, but you could see right here, this is a table of state 1 through state 4 at the different pressures, different temperatures, quality when applicable. Sometimes it doesn't matter. A specific volume, really you don't need the specific volume at a lot of states, but if you're running into a pump, you typically want VDP and you want to use that. We talked about it. So specific volume of the saturated liquid feeding the pump is useful. Enthalpy, the most important, but you can't get it sometimes without working with entropy and quality. All right. Then you get a table of energy transfers. Half the table is zeros. Half the table are negatives. Then the other half, well, not the half of the half is negative, right? And then the other half of the half. But these need to match the sum of the Q's and the sum of the W's. And then finally, you compute your metrics of interest. And in this case, we have a very low backwork ratio often for a good Rankine power cycle, about 1% or even less. That's good as an engineer. What comes out of the turbine, let's feed most of it, 99% of it to the electric generator to make money, sell electricity. The thermal efficiency of the plant is going to be lower than the Carnot. The Carnot had the same pressure for the boiler and the same pressure for the turbine. It came out saturated vapor out of the boiler, but it's a lower thermal efficiency. So on a TS diagram, you want to go ahead and plot these states. This is plotted in this reliable software. You can purchase it. It's used all over the world. It's very reliable. The National Institute of Standard Technology puts it out. Student version for free. Did anybody try it? Yeah, you can. You checked it out. Right. Anyway, here is state 1, saturated vapor at the 8 megapascal. There is state 2. You expanded it. It's constant S. Notice this is the x-axis, S. Hence, S1 is equal to S2. It's a straight line down. And then instead of condensing and stopping, you condense all the way over to state 3, this is state 2 here, is saturated liquid. Okay, but state 4, where did state 4 used to be in the Carnot? That's where it used to be. That's where it used to be in the Carnot. So now I want to find state 4, and so I ask another clicker question. Is state 4 somewhere in the vicinity of this cloud? Answer A. Is it somewhere in the vicinity of this point? Answer B. Or is it somewhere in the vicinity of this point? Answer C. Clicker question. Where is my state 4, which is after the pump? State 3 is into the pump. Saturated liquid into the pump. Where is state 4 on this TS diagram? Yeah. All right. So just like it's a constant S for going through the steam turbine, we knew state 2 had to be somewhere on a straight line, vertical line underneath the state 1. Then that's how we determine where state 2. Well, the pump is isentropic. It's an ideal Rankine cycle. There's no entropy generation in it, right? So it's somewhere along that line. So what do you think about A, the cloud A? Well, that would have had an increase in entropy to go from state 3 over to somewhere like this for state 4. That would mean it's irreversible. Entropy would have been generated in that pump. So we can rule out A, no good. So the only real contenders are B and C. Now, let's take a look. What's on the y-axis? Temperature. This was about what temperature? Do you remember the numeric value of the condenser? At 20 kilopascal? Can you visually see what roughly it is? Give me an estimate. Nearest 5 degrees something, increment. 60 degrees is the number it is. 60 degrees C. That's still pretty warm. But now let's do up here. This was our 8 megapascal. What was this temperature I come across? It was 295 degrees C. You could round it off. You could round it off to almost 300. All right. So now, if you're up in this cloud, like in this vicinity, you would have a hot fluid coming out of that pump. All right. Down here, if you're in cloud C, you have a cold fluid coming out of that pump. A relatively, I mean, still 60 degrees is hot, but it's not nearly 300 degrees C. So what I'm going to do is ask the same question. If you're insane, you can still vote for A. Boom. All right. Somebody asked a question. They say, hey, last lecture, state 4 was right there. Yeah, state 4 was right there for CARNOT. And state 3 was right there on a straight line below for the CARNOT, vapor power cycle. But now we shifted away and we talked about the pump that had this job of taking 3 and going to 4 was an unhappy pump. A pump that doesn't really exist. You cannot buy it. You cannot, I mean, it's a fool's errand to try and design it, okay? So then they said, well, the Carnot is the frictionless cycle that can't be implemented, but how close can we get to it? The Carnot is the frictionless cycle. We can't get to it. But the ideal Rankine is as close as we can get. What you have to do is don't stop there in your condenser. Go all the way over here and move state 3 over there. Now, once state 3 is over there, the question is on a TS diagram, where is the new state 4? Right. And so let's take a look at what they said. They say it's down by C. And it is. It's down by C. Now let's go back and look at this one. And so we got a few people moving away from A. Yes, sir.
Physically impossibly the way it's watering at 300 Celsius above.
Yeah, you're right. Because when we had a bunch of those plots, remember the high pressures? They all tucked in here. The region where it's saturated or compressed liquid is very tight, close to the side of that dome in the TS diagram. This is no man's land. It's like no fluid exists in equilibrium unless you're at some super ridiculous supernova pressure. I don't know. Nothing in my engineering experience or yours either. All right. So you're right. That's another way you could rule that out. Okay. So somebody says, well, why don't you plot state 4? Well, it was there all the time. State 4 is plotted with the same symbol as state 1 and the same symbol as state 2. Can you see it now? Or do I need to zoom in? All right, this is the value of that software. So if we zoom in, this line right here, guess what pressure that is? That's a line of constant pressure of 8 megapascal. Guess what this blue line is a constant pressure of? 20 kilopascal. That's right, 20 kilopascal, 8 megapascal. And what happens to the 20 kilopascal line when it gets to the saturated liquid point? It just scoots down right here. You're saying you didn't plot it. I said it is plotted. It's just so close to the red line that we can't really see it. And we had to zoom in to see the difference between the 8 megapascal subcooled liquid line and the red saturation states of the TS diagram, that side of the dome, saturated liquid states. So this is still S. I know that you really zoomed in, and look at the temperature. So what is the increment of temperature from here to here? 1 degree C. So if I look at it, that does come in good at 60. Can you give me a visual of what the temperature is of state 4? 60.5, 60.4, 60.3. It's not over 61, is it? That's the whole point. So the pump really doesn't change the temperature of the fluid going through it. It only boosts the temperature a little bit. It really boosts the pressure. All right. Now we want to evaluate the pump work. We talked about this last time. So if I have a pump and I bring it in and I take it out, let's call this state 1 and state 2 for the pumps. You can calculate H2. If I was given the final pressure, outlet pressure of the pump, and if it was reversible, then S2 is equal to S1. And some people might say, hey, this is great. And because this is now compressed liquid, you would start to use the table for compressed liquid water, and I think that table is A5. But that table A5 is not very refined. It's like, oh, you're at 10 megapascal or 20 megapascal or something like that. And so a lot of times you would have to interpolate if you really wanted to get H out of table A5 given pressure and entropy. And we're going to go through that in detail in a second. Another method is to say, I'm going to be able to calculate the work that is out of the pump, okay, is equal to a minus the integral V dP. We talked about this last time. Where did that equation come from? End of chapter 6. And I wrote down that equation number, but I don't have it right in front of me, but you should have found that equation. 6.51 something. Yeah, okay. Because the specific volume of a liquid, like liquid water, doesn't change much during flowing through the pump, that can come outside the integral. This is a very easy integral, so we have V sub 1 times P2 minus P1. You calculate then this work of the pump. But there's a little subscript on this. It's called int rev. What does that mean? That means that S is a constant. You don't have any irreversibilities. But this is a great approximation. You don't have to do any double interpolation in table A5. You calculate the work of the pump, and then if you wanted to calculate the H2, it would be H1 minus a minus, which basically you put this, int rev, and put the S there, because it is assuming it's isentropic, internally reversible. Does that make sense? Is that okay? All right. But let's say I do want you to go in and at 80 bar, at that S, which was for this problem, you would come in here and you say, well, I wish it was 75 bar, or I wish it was 100 bar. But if it's because it's 80 bar, I can do a intermediate first interpolation to create a little subset, a pressure table at 80 bar. And in there, I can kind of figure out where this S is. It falls in between these two values and these two values. Hence, I would create an S column and an H column, and I'd do 4 interpolations. First, with respect to pressure, to get H at 40, H at 80 degrees C, S at 40, S at 80, at that new pressure of 80 bar. Okay, that's your first level of interpolation. Here are some of the numbers if you want to follow it. Notice that that fraction, 80 is from 75 to 100, is 20% of the way. Is 20% of the way. Your interpolation is much more accurate if you have a fraction that's either close to 0 or close to 1. You're close to a data point on either side. But if you're near 50% on that fraction, you're getting, where you would expect the most error in the interpolation compared to real data. Because this is just linear interpolation. All right. So then I've constructed this SH subset. I come in here. There's my S. I finally can do the last interpolation with respect to S to get the H. Notice that that fraction is around 52%. Here's that fraction. So I kind of like, oops, I'm right in the middle. So I don't anticipate this to be super accurate. All right? Here are some of the other numbers. But when I compute that work that the pump would give using table A5, it would be 10.6, maybe I should have put the negative sign on there, but I know that this is the outlet, this is the inlet enthalpy. I then pause. I say not table A, it's A5. I just did a double interpolation to find the work of the pump. I could even look at the temperature, do that double interpolation to find this temperature right here. It's about 52% of the way between 40 and 80. It's around 60.98, hence around 61 degrees C. I go to ref prop. This is grabbed off a table, not plotted, so I can get more digits. I then have the constant S, and I have the low pressure, 20 kilopascal, and then the high pressure, and really it fills in the blanks. It's like, oh, I'm going to give it the P and the S, and it fills in the rest. I shouldn't show you this stuff, right? It's like the software makes your life easy. But yes, on the second exam, you can check your work with either ref prop or IT or another software package out there that you find, but you still have to turn in with hand calcs. You can check your work, but you need the hand calcs in the exam, okay? Now, take a look. What about 10.61 versus 8.11? Well, it's different. Maybe it's not that big of a deal, but this would be the more accurate using the ref prop. And instead of 61, it would be about 60.4. Okay. Let's use the approximation VDP. Hey, we're trying to do the same thing. At the end of chapter 6, if you do the integral VDP, you get 8.12. Now, is the approximation VDP closer to what I would trust or the double linear interpolation? The conclusion is just use VDP with a good pump. And it's constant, it's liquid's incompressible assumption. It's easiest to use and it's very accurate. Makes sense? Yes.
Is that, did you get those values for the VDP through interpolating?
No, the pressures are given, and this is the saturation pressure at the 20, so straight out table. Okay, there was a long explanation, but believe me, I get these questions all the way through, even at the end of the final exam. Somebody's, hey, I want more points and blah, blah, blah. And this will be the heart of the discussion for a while. So please, if you're not grasping everything, read the book, talk to friends, visit me, do something to really grasp this concept, but use VDP. So when you move to the ideal Rankine cycle, the turbine is still isentropic, the pump is still isentropic, and what we typically do is we grossly exaggerate the temperature difference between 4 and 3. But believe me, the temperature difference is about 1 degree C or less. Temperature difference. Now, when we compute the thermal efficiency of the Carnot, and it compares and agrees with the simple equation 1 minus Tc over Th, but when we come over here, we compute the thermal efficiency, 34% versus nearly 42%. What do you think? Are they the same? No. Which one's lower? The Rankine. Well, why is the Rankine cycle lower? So, why is the thermal efficiency of the ideal Rankine cycle lower than the Carnot vapor power cycle? Hey, turbine, condenser, pump, boiler, they all had the same kind of components, even though the Carnot had an unhappy pump, but we switched that out with the ideal Rankine. And so you could answer, hey, it isn't. They are the same. If you're insane, go ahead and select A. B, I think there's irreversibilities in the turbine. I think there's irreversibilities in the pump, boiler, or condenser. It's one of those. All right, so let's go back here and say, was this a straight up and down line going from state 1 to state 2 that's in the turbine? Is it a straight up and down line? So S1 is equal to S2. Are there any irreversibilities in the turbine? No. All right. Is this a straight line between 3 and 4, constant S? Yes. Are there any irreversibilities in the pump? No. So let's come over here, and when when in doubt, you just say, I don't like that answer. Done. Now I'm down to guessing between 4. And then you just go, I don't like this answer and this answer. Now I'm down to guessing between 2. So now we're going to guess which one it is. Do we have irreversibilities in the boiler or the condenser? Well, what was really different? Look back here. If I have the fluid condensing, does all the fluid condense at the same temperature in the Carnot? All right. Here's the condensing between 2 and 3. Does all the fluid in the ideal Rankine condense at the same temperature? Yes. All right. Take a look now. All the heat coming in between 4 and 1 for the Carnot, does it all come in at the same T high? In the Carnot, does all the heat come in at the same T high? Yes. All right. Here's 4 to 1. Does all of the heat come in at the same T high? Okay. Which answer do you think is the reason for the difference between the thermal efficiency? What's happening in the boiler where all the heat does not come in at the same TH? Or in the condenser where they all are rejected at the same TL or T cold? Try again. You want to try again? All right, we're done. Okay, that's the best exclamation I could give. The difference was in the boiler, isn't it? So what's happening in the boiler? I'll close this. What's really happening in here in the boiler? Well, you can think of the boiler busted into parts. You're going to take the 60 degrees C water and bring it up to 295, and then once it's at 295, it's saturated liquid, and then you continue to add heat until it goes out at 295, and now it's saturated vapor. You see what's happening in the boiler now compared to, it used to all be 295. So what's happening is I'm bringing in heat just to heat up the cold feed water. Okay, the little bit of heat to get it from 60 to 70, to 70 to 80, 80 to 90, 100 up to 150, 150 up to 200, 200 up to, there's a lot of heat just bringing it in. And that's bringing at a lower temperature. And so some of that heat, so if you think about it, 1 minus TL over TH. If you want this efficiency to be high, you make this low and you make this high. That's good for Carnot. It's still good for the ideal Rankine cycle. Good concept. Bring in all your heat into the working fluid at high temperature. You like to bring it in up here. You hate to bring it in down here. Bad for performance. That's the simple explanation that I can give you on it. We'll drive that point home some more, but let's move forward. So the irreversibilities now you can have in the turbine. Let's just review how you handle the true irreversibilities in the turbine from Thermo 1. So you come in at state 1, you go out at state 2. On a temperature entropy diagram, there's our dome. Let's say state 1 is saturated vapor. And if I had perfect expansion to a lower pressure, that would be state 2. If it's perfect, it's reversible, adiabatic, it's isentropic, we would call from 1 to 2, we could say that's state 2s. But now we have some irreversibilities. So sigma dot divided by m dot's not 0. When you do a second law analysis, you find that the outgoing entropy is equal to the incoming entropy plus if there were any entropy generation per mass flow through it. See that? That's a bad percent there. That's a second law. This is still insulated. There's no heat transfer to the surroundings. So S2, if you have irreversibilities, is greater than S1. The assumption is you still go down to the same condenser pressure. So the low pressure P2 doesn't change. The condenser pressure doesn't change. Well, where's now my actual state 2 on this TS diagram? Perfect. To the right, on the blue line, on that isobar. So it could be where state 2 is now here. It could be where state 2 is there. And if you really had a crummy turbine, maybe it's way out there. But it's somewhere, the standard assumption is on that same condenser pressure line. All right, so they draw it with a dashed line going from 1 to 2. The book usually doesn't put an additional subscript on that 2. I like to put the subscript or additional added T2A. Why 2A versus 2S? Actual outlet condition versus the isentropic. Okay, so 2A could be way out here. If it was, you would have a dashed line. Why do we have a dashed line? Why is that the suggested notation in virtually every thermo book I know? Because the dashed line indicates there are irreversibilities. Hence, when you go back and you do the integral Q dt, blah, 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 you can't do that for this line because it's not a reversible path. Okay, but let's press forward here. So we're going to have a eta subscript t, which is a percent. It's a fraction. It's a measure of the efficiency of that turbine. We were introduced to Thermo 1 to the isentropic efficiency. That's what we're talking about, the isentropic. And it's a ratio of the work that the turbine produces for 2 cases. And it always is less than 100%. It's a fraction, right? So what do you think is going to produce more work out of the turbine? If it's frictionless, reversible, or if I have a bunch of friction, bunch of irreversibilities? So frictionless. So that goes denominator, and the actual is in the numerator. And then from a first law analysis, the work that the turbine puts out actually is the inlet enthalpy minus the actual exit enthalpy. That's just the first law analysis. Just like this was the second law, that's a first law. Okay. And then you have H1 minus H2S. I like to do these in a couple steps. Actually compute what is the work that the turbine actually produces. And then also, what is the work that would be if it had been isentropic expansion through the turbine? Maybe you compute this to be, I don't know, 55 kilojoules per kilogram. And maybe this is 43 kilojoules per kilogram. And then you can do to calculate the isentropic efficiency. Or sometimes you're told that the isentropic efficiency is so much. So you rearrange this equation and you get that the work the turbine actually produces is the isentropic efficiency of the turbine times the work the turbine would produce if there was isentropic expansion. So it depends. Sometimes you're given this information, asked to make that calculation, and sometimes they change it up. But these equations hopefully make sense to you. True? Do the same thing now. Let's review pump. Pump. Okay, we make a schematic of a pump. Let's call it inlet state 1, outlet state 2. Let's go ahead and draw it on a temperature entropy diagram. What do you really want to feed a pump? Saturated liquid. Happy pumps. There's state 1. Where is state 2? We're going to exaggerate it on a TS diagram. TS diagram. But 2 is on this line of higher pressure. All right. So we do a second law analysis, and we find that the outlet entropy is equal to the inlet entropy plus sigma dot divided by m dot. Well, if there's any irreversibilities, where should state 2 actual be compared to state 2 isentropic? Should it be somewhere up on this side or on that side? Answer A or answer B? Answer A or answer B? Clicker question. We're going from 1 to 2. We used to go straight up. Should we now go not straight up, but maybe straight up and kinked over a little bit to the right? If you think that's correct, answer A. If you think it's straight up but kinked over to the left, answer B. Where is state 2 actual? Well, if you look at this equation, there's no way the outlet going entropy can be less than the incoming entropy. Basically, this is just a production, so it's adding. What's our standard assumption about the heat transfer between the pump and the surroundings? 0. It's adiabatic. That's right. So you're going to find that 2 actual will be something over here. And again, I exaggerated 2 actual. It will have, again, a slightly higher temperature than 2S. Not a lower temperature than 2S, a higher temperature because of the friction and the irreversibilities in the pump. All right, and a slightly higher S. The S goes up. Okay, now we have eta of the pump. What is eta? Isentropic efficiency of that pump. So we're going to write this out, that we have the work of the pump and the work of the pump. Now, you can make it where it's the work of the pump isentropic over the work of the pump actual, or you can put actual over isentropic. Let's see if you can figure out if A is correct or B is correct. I killed my clickers. Great. I killed it. So, show of hands, A. Show of hands, B. See, we're not unanimous, are we? Let's do this. The work pump isentropic, will that be less than or greater than the work of the pump actual? The work of the pump actual is greater than, oops, I drew that wrong. Yeah, put it like this, it's easier, the pump. Actual is greater than the work of the pump if it was frictionless and perfectly beautiful pump, you know, it's like reversible. So, what you want is an efficiency that's less than 100%. So guess what? You put the smaller in the numerator and the larger in the denominator. Do you remember this? So that was always confusing to students. Because I look, it's like S is the work of the pump S, but I go back to the turbine, where is the isentropic? It's switched between the pump and the turbine. Why? Well, one is a work producing, one is a work consuming. Okay. So now you can say, well, what is, here, let me clean this up. What is then the equation to get the work of the pump isentropic? The preferred equation is V dP. And in this case, it would be V1, saturated liquid coming in, and that would be P2 minus P1. That'll be a positive quantity. If you want to make it consistent with the book, then it would be P outlet 1 minus 2 with the negative sign, blah, blah, blah. But look, just get rid of the negative sign, take ownership. It's P2 minus P1. It's a positive quantity. That's positive. All right. What about this one? Well, you can do it a couple ways. Often you're given the isentropic efficiency so that you calculate WP isentropic using that equation, multiply it by the pump, not multiply it, divide it by the pump isentropic efficiency, and that allows you to calculate the actual work of the pump. And then the actual work of the pump can be written as H1 minus, not H1, H2 minus H1, or the actual outlet enthalpy is equal to the inlet enthalpy plus what actually went into the working fluid as it flowed through the pump. All right. I've gotten rid of a lot of negative signs, but there you go. Does that make sense? All right. So as we continue this discussion, we now moved away from the Carnot. We're talking about the Rankine cycle. The general theme is to have improved thermal efficiency. What should you do to the boiler pressure? Make it as high as possible, because that increases TH, and that's good for Carnot, good for the Rankine cycle. Also decrease the condenser pressure. Why? That reduces the low temperature at which you're rejecting heat. Good for the Carnot, good for the ideal Rankine. Let's talk now a little bit about superheat. So we have our temperature entropy diagram. Instead of stopping right here at that high pressure and putting it through the turbine, you could actually superheat it, meaning it's coming out superheated vapor at that high pressure. Well, you're bringing in more heat at higher temperature, aren't you? Yeah. That's good for performance. Superheating's good for performance, good for thermal efficiency. Also, when you expand it through the turbine, if you expanded it, maybe you went down to this low pressure, well, you have a pretty low quality. I mean, it may still be 60%, but that means by mass, 40% are in liquid water droplets, which act like little bullets. They don't turn as easily as the vapor inside your turbine. So they smack in the surfaces where the vapor would turn. Not good. So what you'd like to do is you'd like to get it where it expands and maybe a higher quality steam. Maybe 95, 98%, 99% quality. You really don't want the steam to come out superheated, because then you're going to condense it and you're just wasting energy. You really want it to come out in a sweet spot of high quality. So superheating helps that too. But sometimes, let me see if I can expand this a little bit. Let's say I take the same pressure, 8 megapascal, find that line of 8 megapascal right there. Instead of stopping at saturated vapor at 295, almost 300 degrees C, I superheat it to 440. I bring it up, here's 400, here's about 440, I bring it over. Right there is state 1. See that? And then I expand it down to this 20 kilopascal. Well, yeah, it's improved the quality, but I could even improve it more if I expanded it down to an intermediate pressure. Let's pick this pressure, 2 megapascal. Stop the expansion. The temperature would be, around 200 degrees C, but I would then heat it up some more and heat it back up to maybe 440. That's called reheat. Why would that be good for performance? The same reason the superheat. You're bringing in heat at relatively high temperature. Then when you expand it, it's good for outlet quality, the last turbine stage, out the outlet of the turbine. You really want to be over here. So that brings us to the next one, which is reheat. Superheat's good. Good because you're bringing in energy at higher temperature, as well as the quality going out at the end of the turbine is higher. And then the reheat is good. How do they accomplish this reheating? They come out of the turbine and they go back to the steam generator, reheat the steam, and then put it through a second turbine. So maybe this pressure right in here is the 8 megapascal. Maybe this pressure is the 2 megapascal. And then it finally drops it down to 20 kilopascal. That is the way power plants are built. We start by understanding Carnot, what makes it efficient, then trying to repeat that in our real power plants. Okay, now if you plot this on a TS diagram, it's just what I sketched. And it moves the quality at state 4 now coming out of the turbine over, which is really good. Okay. The last one we want to talk about is this one over here. What's happening? You're bringing in this feed water right here. Oh, it's 8 megapascal, but what's the temperature at state 6 out of the pump? It's about 60 degrees C, 61 degrees C. It's pretty cold. At 8 megapascal, it has to be heated up to state 7. That's just intermediate state inside the boiler, where it's saturated liquid. Again, that's around 295 degrees C. So from 60 to 295, I'm bringing in a lot of energy, and it's at low temperature, not good for performance. Then I'm bringing in a lot of heat at 295, then up to 440. And then over here, it's whatever that temperature was at 2 megapascal coming out of that turbine. It wasn't as high as 295, but it was still close. And so it's good for performance. But this is now something to focus on. Let me do this. I know that this is a lot of information, but I think if you grasp the concept first, it'll be better for you. What percent of the energy is brought in here for that steam generator just heating up that boiler to get it up to 295? 30%. You can do some calculations from 6 to 7. 30% of the heat is in the liquid just to get it from 60 to 295. And that's the harder one for students to really grasp. Why does that help performance? Well, this is it right here. Okay. To boil it is 40%. To produce the steam is 14%. All right. Now let's jump to the last one that I want to cover. So I have this cycle. I've already introduced reheat. I believe in that. That's going to be good for performance. How do I achieve getting this temperature into the boiler right in here, the steam generator? How do I achieve that to be higher than 60 degrees C? Burn more coal. Well, okay, but coal is expensive. Burn something else. Okay, but use solar panels. Yeah, but let's do something that's going to work in the middle of the night. Okay, as well as when the sun is shining. And so you want to introduce something right here. And you want to get the fluid that's 60 degrees be warmer so that when it finally is fed into the boiler, feed water into the boiler, it's warmer than 60 degrees C. Well, this steam right here that was extracted after the first expansion, maybe you bring it out like this, and then you divert some of it. Not all of it. Divert 20% of it, 30% of it. What is that going to do? Well, it's pretty hot. From an exergetic point of view, it's hot, but it doesn't have a lot of exergy. So basically, it's better to do an exergetic analysis of this. But energy point of view, it works just as well. Then we put it into a feed water heater. You can put an open feed water heater, the simplest. So what's an open feed water heater do? Well, you have this pressure right here at state 2. That's maybe 2 megapascal. After this first pump at state 2, at 6, it's like 2 megapascal. And then going out at state 7, what do you think the pressure at 7 is? the pressure at 7. If the inlet pipe and the inlet pipe are at 2 megapascal and it's a feed water heater and it's open, which means they just mix. That's all they do is just mix. What do you think the pressure at 7 is? 2 megapascal. Then that pump boosts it to 8 megapascal, or the highest pressure. All right. So this works. So what you do is you divert a fraction. Maybe you divert 20%. Well, then what remains to continue into the process and get reheated and get, well, about 80%. And so what they do is they say, well, let this be y. What is y? Another variable. And y is that mass fraction that's diverted to the feed water heater. Okay, so y could be 20%. Then guess what is going over here? 1 minus y. Isn't 1 minus y then 80%? And then see if you follow the concept. Let's let y be 25%. What is the 1 minus y that then goes into the second turbine? 75%. It's 1 minus y. All right. Well, we're going to pick up in how to calculate y. And I'll just tell you right now, it's a mass balance and an energy balance around this open feed water heater. A mass balance and an energy balance around the open feed water heater tell us the best y. The other thing is, the only other thing you have to really understand is what makes for happy pump 2. I better feed it saturated liquid at state 7. That's what makes a happy pump. So knowing that and being able to accurately do a mass balance as well as an energy balance around that open feed water heater gives us what y should be for that plant. Change pressures, change temperatures, and then you'll get a different y mass fraction that's diverted. Right now I'm going to pause and give you guys a quiz, okay?